We will now look at a few examples of the of application of the dominated convergence theorem. So first example, it's called the Fourier transform. So Rn equipped with Lebesgue measure so given two vectors x equals x1 xn and y equals y1 yn, the inner product x dot y is given by sigma xi yi, I equals 1 to n. If it's complex, then of course you put yi bar if in case you're dealing with Cn. Otherwise in Rn we just write f of x. So let f R to R integrable. Then the Fourier transform so this is denoted by f hat evaluated at xi is equal to integral over Rn e power minus 2 pi I x dot xi dm fx dmn of x. Because x and xi are involved, I am writing the variable along which we are integrating. So maybe here, since I is now reserved for the imaginary number, let us say xj yj. Okay, so this is called the Fourier transform. So first of all, it is well defined because mod f hat xi, so when is therefore less than or equal to, by a result we have already proved, mod e power minus 2 pi I x dot xi mod fx dmn. Now this is of course equal to 1, and therefore this is less than or equal to integral and mod fx, and therefore this is f is integrable, and therefore this is finite. So f hat is well defined and it's a bounded function, and namely the L infinity norm of f hat is less than or equal to the L1 norm of the function f. Okay, the integral of the function mod f. Okay, so now we also have that e power minus 2 pi I x dot xn f of x will converge to e power minus 2 pi I x dot xi f of x as xn converges to xi. So this is for xi in Rn. Okay, and mod of e power minus 2 pi I x dot xn f of x is less than or equal to, again modulus of this is equal to 1, and this is less than or equal to mod f x, and f is integrable. Therefore by the dominated convergence theorem we get f hat xn converges to f hat xi. That is, f hat is a continuous function. So given an integrable function, the Fourier transform produces a continuous and bounded function. In fact, it is a bounded and uniformly continuous function, which can be proved also. Okay, so that is one example. Example again. So earlier when we saw that Aij in R 1 less than or equal to ij less than or equal to infinity, and this is a double sequence. So if Aij's are all non-negative, we saw sigma I equals 1 to infinity, sigma j equals 1 to infinity aij equals sigma j equals 1 to infinity sigma I equals 1 to infinity aij. Not true in general. You have 1 minus 1 0 0 0 1 minus 1 0 0 1 0 0 minus 1 then 0 and so on. Let us go on like this. Then if you look at sigma aij, as j goes from 1 to infinity, this is 0 for all I. So sigma I equals 1 to infinity, sigma j equals 1 to infinity, aij equal to 0. But sigma j equals 1 to infinity, sigma I equals 1 to infinity, aij, this is always plus infinity, because the first column gave you infinity and then you are only subtracting one at a time, and therefore this is giving you infinity, and therefore this does not agree in general. So we are now going to give you a sufficient condition when the result is in fact true. So let us assume, for each j in n, you have sigma I equals 1 to infinity mod aij is convergent, and so that is less than or equal to bi, and sigma I equals 1 to infinity, sigma first of all less than or equal to bj, j equals 1 to infinity bj is also finite. Okay, so we assume these two conditions. So for every j, sigma I equals 1 to infinity mod aij is convergent and it's less than bj, and sigma bj is itself a convergent series. So now let us take x to be the natural numbers. S equals power set of n, and mu equals counting measure. And let us take fi of j equals aij. Okay, and let us take f to be equal to sigma I equals 1 to infinity fi. So we have, what is f of j? F of j is sigma I equals 1 to infinity of aij, and define g of j equal to bj. Then sigma bj is finite, and this implies that g is non-negative integrable function. Let us define gn to be equal to sigma I equals 1 to n fi. Then gn tends to f. Okay, and you have mod gn at any j equals mod sigma I equals 1 to n fi of j, and that's less than equal to mod sigma I equals 1 to n aij, and that's less than equal to sigma I equals 1 to n mod aij, and that is therefore less than equal to bj equal to g of j. So gn converges to f, and gn is bounded by g, and g is integrable. So gn converges to f, mod gn less than or equal to g, and g integrable. Therefore, by dominated convergence theorem, you have that integral gn converges to integral f. So let's see what, so d mu over n, d mu over n. So let us write down both these sides. So the right hand side, so integral f d mu over n is nothing but sigma j equals 1 to infinity f of j, and that's equal to sigma j equals 1 to infinity sigma I equals 1 to infinity aij, because f of j is sigma I equals 1. Okay. Now what about integral gn d mu? Integral gn d mu over n is equal to sigma I equals 1 to n sigma j equals 1 to n aij, because gn is sigma I equals 1 to n fi. So gnj is, you have to sum over all j, and therefore this, and this, it's a finite sum, this you have this. Therefore limit n tending to infinity sigma I equals 1 to n sigma j equals 1 to infinity, sorry, aij. This is just finite series, and therefore this is nothing but sigma I equals 1 to infinity sigma j equals 1 to infinity aij, and therefore you have, so limit n tending to infinity integral g and d mu equals integral f d mu, and that is exactly saying, so we have computed both sides, and that is equal to sigma I equals 1 to infinity sigma j equals 1 to infinity aij is equal to sigma j equals 1 to infinity sigma I equals 1 to infinity aij. So this hypothesis which we made here allows us to interchange the order of summation in general. Of course, this result is not true as you saw. So this comes from the dominated convergence theorem. So the non-negative case came from the monotone convergence theorem, and the general case comes from the dominated convergence theorem. So proposition x s mu measure space, f integrable function. Given epsilon 0, there exists a delta greater than 0 such that mu e less than delta e in s implies integral over e mod f d mu is less than epsilon. So there is some kind of continuity, and we call this in fact absolute continuity. So if the function is integrable, then you take the indefinite integral of mod f, namely integral over any set e mod f d mu. So if the measure of e is small, then the integral can be made small. This is the theorem. Okay, so proof. Step 1, assume f bounded. So mod f is less than or equal to some m, and therefore integral over e mod f d mu is less than or equal to m times integral over e, and therefore that is just m times mu e. Therefore if you choose delta e equals epsilon by m, then we are through. Step 2, define fn of x equals mod fx if mod fx is less than or equal to n, and n if mod fx is greater or equal to n. So this is a cutoff function. So you take the function, when it reaches the threshold of a value n, you cut it off and then fix it as n. Then of course fn is now bounded, it is bounded by n, and fn in fact increases to f, and fn is non-negative. So by the monotone convergence theorem, we have that integral fn d mu increases to integral f mod f d mu over x, and this of course being integrable is finite. Therefore there exists a capital N such that for all n greater or equal to capital N, you have integral over x mod f d mu minus integral over x fn d mu can be made less than epsilon by 2. So in particular you take capital N, and by step 1 there exists a delta such that mu e less than delta greater than 0 of course, mu e less than delta implies integral over x mod fn d mu is less than say epsilon by 2, since fn bounded. And that tells you that integral over x mod f d mu is then okay. So now integral over e mod f d mu is less than or equal to integral over x mod f d mu which is then mod f d mu minus integral over x fn d mu plus integral over e fn d mu. Sorry. Just a minute. Okay, so let me score this out. So mod fn over x d mu is bigger than or equal to integral over e mod fn, sorry, not mod fn, fn d mu. So you have minus of this is therefore less than or equal to minus of this. Okay. Okay, that now we are through. So integral over e mod f d mu is less than or equal to integral over x minus integral over e fn d mu plus integral over e fn d. Okay, now this is less than epsilon by 2, this is less than or equal to integral over x mod f d mu minus integral over x fn d mu, and therefore this is less than epsilon by 2, and therefore you have less than epsilon.